All right, so let's get started. We're still talking about error detection codes. We started briefly about that last time, so we'll finish that off today. And then we will talk about how to use these error detection codes to provide reliable transmission over a network where errors occur. Okay, so that has to do with these retransmission protocols. And in these retransmission protocols, error detection is a crucial part of it. Okay, so what we did last time we met was to talk about block encoders. Block encoders we use both for error detection and error correction. In this course, we will concentrate on error detection. Error correction is the process of detecting that errors have occurred and fixing them. Error detection is more of the is about finding if errors have occurred or not, and then one use that information for other purposes, as we will see later today. I mean, at the end of the day, what we would like to do, anyways, is to provide error-free transmission. But these block codes, NK block codes or block encoders, means that we take an input of k bits and outputs an output of n bits. So the input here is k bits and the output is n bits. And n here is in practice always larger than k. The inputs here we call information bits. The block of input bits we called a information word, information block, or information vector is the same thing. The output bits are called code bits or coded bits, and if we block them together we get the code word. And the code word consists then of n bits, and the input block contains k bits. Since the input contains k bits, we have 2 to the power of k possible inputs, and for each of these inputs we produce one output. And for practical purposes, all the outputs, for different inputs, we have different outputs. You never have, in practice, a block encoder which takes 2 different patterns and outputs the same pattern here. Okay, so if we collect all the possible outputs in this curly C, the set curly C, which is known as the code, we have then 2 to the power of k possible patterns here. C1, C2, up to C2 to the power of k. So these are the code words. The code rate is the ratio between the number of input bits to the number of output bits. And we can think of that as measuring the number of information bits per coded bit. A systematic code is a particular encoder or a particular code where the first k bits in the code word is equal to the input. Okay, so we take the input and we just copy that down into the code word, and then we have some check bits or parity bits at the end, which is a function of the first bits. And that function is whatever this block encoder has defined. So there is some mapping from input to output. In systematic codes, we just copy the information bits at the beginning of the code word. And this is very practical when it's time to decode the information bits, because if we receive a pattern of n bits, if we want to figure out what is the information bits corresponding to those, we just have to read out the first k bits. So very practical. Okay. We then introduced the notion of Hamming weight, and the reason for this will be maybe a little bit more obvious soon. It has to do a little bit about figuring out the capabilities of this block encoder to do things which are good. So the Hamming weight is the number of ones in a binary vector. So notation-wise, W for weight and H for Hamming, and U is a vector of binary numbers. So it's simply the number of ones in U. Okay, so that's the Hamming weight. We can think of that as the length of the binary vector. Okay. The Hamming distance is between 2 binary vectors is the number of different bit positions. Okay, so to make this a little bit clear, the Hamming distance, D for distance, H for Hamming, U and V 2 binary vectors, is the number of bit positions in U and V which are different. Okay? And if we think about that, we can calculate that through the Hamming weight by just taking U plus V, where plus here is modulo 2 addition. Okay? Which means that O plus here, or this plus sign here, is modulo 2 addition, or XOR if you like. So if we take two bits, U and V, and we add them together, we get 0 when U is equal to V, and 1 when they're different. So this vector U plus V is a vector where the 1s are in those positions where U and V differ, and 0s where U and V are the same. Okay? So U plus V is like indicates those positions where U and V differ. And then we take the Hamming weight of that, and then we get the Hamming distance. Okay, so the minimum distance of a code is a very important parameter or measure of goodness of a code. As we will see shortly, so the minimum distance is the minimum Hamming distance between two different code words. Okay. So we just look at all possible code words, distinct code words. We measure the distance between them, and we take the smallest number, smallest distance, and that's the minimum distance. And we want the minimum distance to be high, as we will see. So if C is the transmitted code word, then the received bits is what we transmitted plus an error pattern, where the error pattern, if it's 0, that's fine, because then C plus 0 is just C, and then Y is equal to C, and then there's no problem. But E here is the error pattern, and it has 1s in the positions where there are errors. Okay, so if E is equal to say 0, 0, 0, 1, 0, 0, 1, 0, it means that in total there are 2 errors in the transmitted code word, and they are at this position, the 3rd position, and in the 6th position. Okay, so it tells us both how many errors that have occurred and where they are. Okay. Question?
Yeah, the notation you have for the E there, is that just to denote that it's a vector?
Yeah, so the boldface E is a vector, where the individual elements of the vector is E0 or E1 up to En minus 1, or sometimes it's E1 for the first one and then En for the last one. So this is a binary vector 0 and 1. Oops. 0, 1, and there's N of those. Okay. All right, so, and then Y, the Y vector is just Y0 up to Yn minus 1, where Yk, the kth of them, is just Ck, the transmitted code bit in the kth position, and the modulo 2 addition with the kth element of the error pattern. Okay, so the weight of the error pattern or error vector is the number of errors in the code word. Okay, and then okay. So the receiver for error detection, and this is, this is a crucial statement. So this one we need to remember always. So if we want to do error detection and we get Y, okay, so the received pattern is Y. So we look at Y, a bunch of zeros and ones, and we want to say, okay, is this what was transmitted or is it not? That's error detection. So either we accept this as the actual bits that were transmitted, or we say that there is some error in this one. Okay. So we need to make a decision here. And the decision is quite natural, actually, because we know what is transmitted are code words. So if we receive something which is a code word, then we assume that everything is okay. And then we say no errors occurred. However, if we receive something which is not the code word, then we are sure that something bad has happened, right? Because what's transmitted are code words, and if we receive something which is not a code word, then something bad has happened, an error has occurred. So error detection principle is very, very simple. We just look at the bits we get and see if this is a valid code word. If it is a valid code word, we accept it. If it's not a valid code word, we don't accept it. We say an error has occurred. Okay. Now, for a code with minimum distance d-min, it's easy to show that all error patterns with weight, which is less than d-min, are detectable. So we will always find these errors. Okay. So note that there is a strict inequality here. And remember that the weight of the error patterns is the total number of errors that have occurred in the code word. Okay. So if the total number of errors is less than d-min, we are sure to be able to detect those at the receiver. Okay. So that's why having a high d-min is preferable, because then we can catch. So if d-min is 3, for instance, we can catch all 1-bit error patterns and 1 2-bit error patterns, right? If d-min happens to be 4, we can also catch all the 3-bit errors. All of those patterns, right? Okay. So if C is the transmitted code word, then for all C in the code, if we say that E is detectable if C plus E is not a code word. Okay, so I'll take that again. I mean, we transmit one of the code words, and we want to characterize error patterns as being detectable or undetectable. And the detectable ones are those who perturb the transmitted code word into something which is not the code word. If it perturbs it into a code word, then the receiver will accept it and not detect that error. Okay? So to say that E is detectable is to say that if we take any code word and add that to E, we get a pattern which is not a code word. If this is true, then we declare an error at the receiving end, right? Because if the received word is not a code word, we say error, right? So all error patterns for which this is true, we say that these are detectable. Okay. So actually, to say that we can guarantee to find all error patterns with weight less than d-min is fine. We can do that. But there are also many other error patterns that we can actually detect. Okay, so we can detect many, but not all error patterns which have weight greater or equal to d-min. Okay. Now, so what is a good code? A good code is something which has a high minimum distance. We argued for that. And then we will shortly talk about something called burst errors. And you should have a good ability to catch those. And also a good ability to detect completely random error patterns. And we'll talk about that shortly. Right? So these are the 3 things that a good code should do. You should catch, you should have a high minimum distance and good ability to get burst errors and completely random bit error patterns. A good code also for implementation should have low complexity. It should be easy to do the encoding and decoding of it. And also we would like it to have high rate. And the reason for this is that if it has high rate, if the code has high rate, it means that we are not adding so many parity bits. Okay, so or check bits. Remember that these bits are not carrying information per se. They're just used for error detection purposes, and we want to make those small. Okay, this is an overhead, right? So for efficiency purposes, we would like the code rate to be high. Okay, so high rate and low encoding and decoding complexity. So codes which are very commonly used in practice are something called singularity parity check codes, internet checksum and cyclic redundancy codes, or CRCs, and we'll talk more about them today. Okay, questions so far? No. Okay, so let's now talk a little bit about these different types of errors that can occur on a channel and what the code properties of the code which make them possible for us to detect them. Errors will occur, okay, but the question is, how do they occur? Or more precisely, can we find a statistical model for characterizing when and how they occur? So we will talk here about error models. And there are essentially three models that we will talk about. The first one is when we have independent bit errors. So this is similar to, if you remember how we characterized the transmitted information bits, we said that if the bits are equally likely independent, this is essentially the same model, except that bit errors are okay. So let me write this down and then maybe talk about it later on. Okay, so we model the error pattern. So this is the error vector. It consists of n bits, zeros and ones. Okay, zeros where there are no errors and ones where there are errors. So we characterize the error as being random, and the randomness comes essentially from the channel noise. If you remember if we have a noisy channel, then we will have errors and they will occur randomly. So if we want to characterize the error pattern, we would like to characterize the probability that the error pattern takes on some specific vector of u. So u is just a sequence of zeros and ones, n of them, and we would like to calculate what is the probability that e takes on the value u. Okay, so e here is the random thing, it's the random vector, random error pattern, and u is just a sequence of bit zeros and ones. And we would like to calculate the probability for this event. So this can be written as the joint probability that the first bit, E0, is equal to U0, where E0 is the first element in the vector E, and U0 is the first element in the vector U. And then we just continue here until the last one, which is En minus 1. We have n bits in E and n bits in U. And since we start to number from 0, the last one is En minus 1. Okay, that this is equal to Un minus 1. So we're interested in calculating this probability. And if we have independent bit errors, then we can write this as the product of the individual bit events. So it's the probability that E0 is equal to U0 multiplied with the probability that E1 is equal to U1. And then we keep on multiplying factors of this nature. And the last factor is then the probability that En minus 1 is equal to Un minus 1, like this. Okay. You remember back when we talked about pulse amplitude modulation and QAM, we calculated the probability for symbol error and then also say something about the probability of bit error. So if we have then the bit error probability for whatever modulation format we have, we can say that we can characterize the probability that E is in error or a certain E occurs. So to be specific, let the probability of the mth one, the mth position in this error pattern, the probability that this is equal to 1, this is the probability that there is an error in the mth position in the error vector. Okay, and we say that this is equal to p, okay, some number which is not dependent on m. So errors occur with the same probability regardless in which position we are. So this is then P here is the probability of bit error. And we see that it's the same for all bits. I mean, same for all bit positions, if you like. Now, if this is the case, then this probability that we're looking for, that E is equal to U, is just the probability that the Hamming weight of E, that is the total number of errors in E, okay? So that's the probability that those occur, and then it's multiplied with the probability that the rest of the bits are correct. And so we have here n minus Hamming weight of E So here, let's go through this again. So we're looking for the probability that the error vector takes on a certain bit sequence here, U. Okay. It turns out that the bit positions here, where the errors occur, is not important. Only the total number of errors is important. So under this assumption that all errors occur with the same probability. So the probability that E takes on U is the probability that W, I'm sorry, so this is wrong. It should not be E here, it should be U. So it's the probability that if we look at the vector U and count the number of ones in that, okay, these are the number of errors that should occur, and then n minus the Hamming weight of U is the number of positions where there are no errors. And we know that the probability for making an error is P, and if we have the Hamming weight of U such events, then the probability for exactly these number of errors is P raised to the power of the Hamming weight of U. Okay, and then the rest of the bits are correct, and a correct bit is transmitted with probability 1 minus P. So we have 1 minus P n minus the Hamming weight of U. So a small example here to maybe clarify things. So let's calculate the probability that E is equal to 1, 0, 1, 0. Okay. So let's go through the bits one at a time and figure out what is the probability for each of the bits. So we said the first bit should be an error, right? The second bit should be correct. The third bit should be an error. And the fourth one should be correct. Okay. So the probability for a correct bit is P. Okay, so this is the contribution from the first bit position. The probability that the second bit, and the contribution from the second bit is that the second bit should be correct. So it has a factor of 1 minus P. And then third bit is P, and then the fourth bit is 1 minus P. Okay. So we have a factor here, one factor per bit position. And we simply go through them. First one error, second one okay, third one error, and fourth one correct. So it's P times 1 minus P times 1 minus P. Okay. And clearly this is equal to then p squared times 1 minus p squared. Okay. We'll take one more example here. Probability that E is equal to 1, 0, 0, 0. What is the probability for this? Well, the first one is in error, so that's a p. And then we have a factor of 1 minus p, because the second bit was correct. And we continue for the third and the fourth bit. So we see here that we get 1 minus p. We get 3 of these factors, so it's 1 minus p raised to the power of 3. Okay. Now, if we look at the factor in the first example here, the factor 2 here is equal to the Hamming weight of u. Right? So here we have, if we want to be explicit, we have P1 here in the second example. So P1 here is the Hamming weight of u in this case. Right? And the factor 3 in this example is because it's n minus the Hamming weight of u. N is equal to 4 in this case. We have 4 bits. And we had 1 error. So this is 4 minus 1 is 3. Okay. So this justifies the general expression for the probability that E takes on a specific pattern U is simply P to the Hamming weight of that pattern, U, the U pattern, times 1 minus P n minus the Hamming weight of that pattern. Is this reasonably clear? Okay. So what we're looking for now is also, so now we know the probability of individual patterns here. And we see it doesn't matter where the error positions are, it's only the number of errors which is important. So if we want to calculate, say, the probability that the Hamming weight of the error pattern is equal to some number L. Okay. That is the probability that exactly L bit errors have occurred. Okay, so what is this? Well, we know that the probability that for an error path, so an error pattern with L bits in it, the probability for this to happen is P to the power of L, because there are L bit errors, and then it's 1 minus P n minus L. So n minus L bits are not in error. So the probability for one particular pattern with L bit errors is PL, 1 minus P raised to n minus L. However, we have also many of these patterns, right? We just don't have one bit pattern with L ones in it. Actually, the number of patterns we have is L choose n, or the binomial coefficient L over n. Okay, so if we have an n-bit pattern, there is L choose n of those who have exactly L ones in it. Okay, so L over n is L factorial n minus L factorial times L factorial. This is all wrong. Okay, let me try again. Okay, it's n factorial, n minus L factorial times L factorial. Like this. Okay, so it's binomial coefficient. So if we go back to our example here, where we have n is equal to 4, so then the probability, the probability that the Hamming weight of the error pattern is equal to, say, 3. What is that equal to? Well, it's equal to the probability that E is equal to an error pattern. So this is a 3. Error pattern with 3 ones in it. Okay, and one such pattern should be, well, 0, 1, 1. 3 ones like this. That's one possibility. But there is also other possibilities. The probability that E is equal to another pattern, say 1, 0, 1, 1. And there is more patterns that E is equal to 1, 1, 0, 1. And then the fourth one is actually, plus the probability that E is equal to 1, 1, 1, 0. Okay, so these are the possible 4-bit patterns with exactly 3 ones in them, right? So there are 4 of those. It's easily checked, right? The probability for all of these events, okay, so the probability that E is equal to this pattern is equal to the probability that E takes on this pattern, and this pattern, and this pattern, because that probability only depends on how many ones there is in the pattern, not the specific pattern itself. Okay, so in this case, let me continue here a little bit. We have 4 of those, and the probability for 3-bit errors is P3 times 1 minus P to 1. Okay. So this example here justifies the general expression. Oops, sorry, I don't want to do that. I want to do this. Justifies this expression that we have L2. Sadly. Sorry for this. It should be N, choose L, right? We have N and we choose L. I think the equation is correct though. Okay, so the general equation here that the probability that we have exactly L bit errors is N choose L, P to the L, 1 minus P, N minus L, which is exactly what we had here in this example. Questions on this? Okay. I know from experience that this is a little bit tricky, right? So you want to go home and look at these equations and understand the notation and what is the meaning of E and U and Hamming weight, and then also not forget the binomial coefficient in these type of calculations. Because what we can do now is we can calculate the probability that we have L bit errors for any L. Okay, and if we want to compute, for instance, that the error pattern has less than d min ones in it, we can do that by simply adding these probabilities together, and then we have a notion about how often we are able to guarantee find errors. Okay, so I think there will be some examples in the exercises to do this. Okay, so. But going back to the big picture here, what are we talking about? We are talking about error models. So this is one particular error model where bit errors occur independently in the code word with the same probability for each of the positions. So P here is not 1/2, right? That would be a horrible channel. But P is maybe 10 to the minus 3 or 10 to the minus 6 or something like that. It's a fairly rare event. if everything goes well. Okay. But there are more error models. And the second one that we will look at is something where all error patterns occur with the same probability. Okay. So what do we mean by that? So equally likely error patterns. Remember that we would like to say something about the probability that the error E takes on some binary vector U. Okay, so that's what we're looking for. With equally likely error patterns, we say that these probabilities are the same regardless of U. So no error pattern is more likely than anything else. Okay, so what is then this probability? So E here is n bits. So we have, how many possible E's do we have? 2 to the power of n. All of these are equally likely. Hence, the probability that we take on one specific U pattern is 1 over the number of possible possibilities, right? So it's 1 over 2 to the power of n. So let me take that again. So here, the probability that the random bit error pattern takes on a specific pattern, U, is the same for all U. So it's 1 over 2 to the power of n, and it has to be 1 over 2 to the power of n, because these are the number of possible U's. Okay. So, and this is in stark contrast in what we had before, where we say that the bits, the individual bits, had errors independent of each other. Okay. Here we say that the patterns of all possible patterns are equally likely. So it's either the bits or the patterns. So this is 2 extreme cases, I would say. So this error could occur when we say we transmit a code word and it's completely lost. And so what we receive is just noise. Okay, that could happen. It could happen, for instance, when we have a hardware failure, or when a cable is cut or something like that. The receiver still tries to decode something, but it only decodes noise and it's all random, right? And we still want to be able to detect those events. What are we actually looking at here is we would like to detect the probability. Okay, so so the probability of undetected errors. Detected error. So what is this? Well, it's PUD, and it's the probability that C plus E, so this is the receipt pattern, right? We transmit C, and we get some error E, that this is equal to, which is in the code, given that E is not 0. Okay. So if the error is not 0, however, the probability that C plus E is in the code, then we would declare that there is no error, even though there were an error. Okay, so this is the probability of undetected error. Okay. So let's look at this probability that C plus E is a code word that is in the set curly C. Sorry, let's actually look at this probability rather. The probability that C plus E is some pattern U. Okay. Then this is equal to, and we do this trick which is nice with binary things, is that if we add, subtraction and addition is the same. So if we want to subtract C from the left-hand side here, we can just add C to the left-hand side, and then we need to add C to the right-hand side. So we have here C plus E, that's the left-hand side, equal to the right-hand side, which is now C plus U. Okay. The beauty here is that C plus C is equal to what? 0. And 0 plus E is equal to the same. If you add 0 to something, you don't change it. So it's the same in binary arithmetic. So 0 plus E is E. So this is equal then to the probability that E, which is on the left-hand side, is equal to some pattern, let's call it U prime, where U prime is C plus U. Okay. So what do we know about this probability that E is equal to U prime? Well, we know that the probability that E is equal to any pattern U is 1 over 2 to the power of n. So we can actually calculate this as being 1 over 2 to the power of n. Okay. So returning to our problem now of undetected error, then this is approximately equal to the probability that C plus, C plus E is in the code. So here we are now also counting the probability that E is equal to 0. But since that happens with probability 1 over 2 to the power of n, it's negligible in the whole thing. So we just overestimate the probability of undetected error with the slightest fraction. Okay, so, but if we're interested in this probability on the right-hand side here, we can actually calculate that now, because we know what the probability of C plus E is equal to U, some specific U. We know what that is, and it's 1 to the power of 1 over 2 to the power of n. And this is true for any pattern U or U prime. So the probability that C plus E is in the code, we know that the 2 to the power of k words in C. So we have 2 to the power of k possibilities of code words, and the probability that E is equal to one of these code words is the same. So we have 2 to the power of k divided by 2 to the power of 2n. Okay. So this is the probability of undetected error. Or we can write this also as the 2 to the negative n minus 2k like this. Or if we like, we can write this as 2 to the power of 2n minus k like this. It's all the same. Okay, so the probability of undetected error for the model where we have equally likely error patterns is very simple. It's 1 over 2 to the power of n minus k. So what is n minus k? Well, n is the length of the code word, and k is the length of the information word. So n minus k is actually the number of check bits. Okay. Number of check bits.
Could you say again what k was?
K is the number of bits in the input to the encoder. So it's the number of information bits. Right. So if we want to have good protection against equally likely error patterns, the thing to do is to make n minus k large enough. Okay. So if n minus k is like, say, 32 or something like that, then we have 1 over 2 to the power of 32, which is roughly, I don't know, 2 to the 32, what is that? It's 2 to the 10 times 3, roughly, right? So it's like 10 to the 3 times 3, so it's 10 to the 6 or something. So it's 1 in a million, right? With 32 bits. Or if that's not good enough, maybe we have 64 bits. And then it's super low. Okay, any questions on this error model? Okay, so let's take a break, and then we have one more error model to do.